So the question we're dealing with in this video is, does the set of direct proportions, that's functions in the form f of x equals k times x, where k is some number, form a group under addition? Another way you can say that is f of x equals kx plus a group. So is that set a group? So what we're really asking about that is whether this set, when we add with it, follows all four group axioms. So just as a reminder, those group axioms are closure, meaning that when you take two direct proportions, ax and bx, and add them, you get a third direct proportion. We can call that cx. It doesn't matter what letters you use, by the way. The second group axiom is associativity. So what that means is when you take three direct proportions and add them, there are two different ways you can do that. You can add the first two first, or the second two first, but either way you should get the same thing. Identity means that there's a direct proportion that we can add to any other without changing anything. So I'm going to say that capital IX, where that's our identity proportion, plus AX is just the same AX. Oh, and one thing I want to point out, we're not saying that A is 5 and B is 3 or anything like that. We're saying that A and B here are just completely generic. A, B, and C here are just completely generic. C is nothing to do, actually, with this right there. Those are not equal. We're not doing these calculations with each other in any way. And then inverses. So for any proportion AX that we want to pick out, there's some opposite of it, and I'm going to call that ZX because Z sounds like a good opposite for A. It's the other end of the alphabet, that we can add together to get back to that original identity element. So what we're going to do is try out each of these one at a time and see if they're true. So what we're really saying with this formula is for any pair AX and BX, we can find the needed CX. So let's see how we would do that. So let's say that A was 2 and B was 4. So if we had 2x plus 4x, the way we would usually think to do that is to combine like terms. So we would get 6x. So 6 would be 2 plus 4. Now this sure looks like it's in format of a direct proportion, like C equals 6. Now I just want to make sure to point out, though, that just because we find an example where it works doesn't mean it'll always work. So let's try another example. 1/2 x plus 8x. Well, knowing what we know about decimals, one way we could write that is 8.5x. So again, 8.5 could be our value of C if 1/2 is our A and 8 is our B. So it sure seems like this works. And the way we came up with these examples gives us a formula to help us find CX so that it'll work how we want to and give us the results we need. So here's what I'm going to do. I'm going to say, okay, we have AX plus BX. And the way we do that in ordinary algebra that we've probably done before is by combining the like terms. So we have A plus B times X. And so then let C be whatever we get from adding A plus B. And so then this is just CX, how we want it to be. And so it works. We've got a formula for doing sums. So closure works. When we add two direct proportions, we get another direct proportion. So we followed that axiom. Next up is associativity, meaning that if we have three direct proportions that we're adding, we can do that in either order, the first two first or the last two first. So what we're saying here is that AX plus BX plus CX is AX plus BX plus CX, regardless if we have parentheses here and do that first, or instead choose to do that one first. So what I'm going to do is take this side of the equation. First I'm going to simplify it, then I'm going to try to re-expand it to make it look like this side. So we already decided that we should combine the like terms. So instead of this right here, ax plus bx, I'm going to have a plus bx. Now to that we still need to add cx. Okay, now what I'm going to say is, since we're adding these things, we're still adding the a plus b first, but then the c gets added on also after. So we've got two direct proportions here. And so we've got a plus b getting added to c on x. Okay, so now that's the whole thing simplified down. It doesn't look that simple because we're doing this with formulas, but if we had numbers in here, we would just have like a single number. So now what I'm seeing is, one thing I know is that in ordinary addition, you can add in any order. If you pick up one rock and then two rocks and then three rocks, you have the same number of rock as if you picked up two rocks and three rocks and then one more rock. You still have 6 rocks. So I can say, okay, I'm going to pick up B and C rocks first. And then pick up my A rocks. And that's going to tell me what direct proportion I'm dealing with. Well, now I'm going to think about working backwards. How could I have gotten this? Well, one way that we could get this A plus B plus C is if we'd had two different direct proportions in the first place, such as an AX and a B plus C X. And this is just kind of the opposite of what we did right here in this step, where we condensed everything down to one direct proportion. Now we're re-expanding it to two direct proportions. But we can expand on that even a little further. This B plus C could be what we got from adding together two smaller direct proportions that had a BX and a CX being added together. We can see that if we added those two together, we would get that. And so it also makes sense, though, that since this was the first thing done, these here would have been combined first. Now we have exactly what we had been trying to get as our right-hand side. So we think that this whole equation has been true all along. And we think that it's something that's required to be true because of things that we know about the way we add numbers. So yeah, we believe in associativity for these AX, BX, and CX. But remember, those are just, A, B, and C could be any number, so we believe that this is going to be true always, anytime we're dealing with direct proportions. So, associativity is true. We're halfway there. The next thing we're going to deal with is the idea of an identity element, so that IX direct proportion, that we can add to any direct proportion, and it doesn't change what we had in the first place. So that's reminiscent of 0, like how 3 plus 0 is 0, and that's going to help us. So one thing we know is that this is acting kind of like a 0, like 0 plus 3 is 3, 0 plus 2 is 2, 0 plus 127 is 127, and that's never going to be different. There's no exception because of just what 0 is. So since it reminds us of 0, the thing we're going to try is to let I equal 0. Now, one way we show that a thing exists in math quite often is to find it and say, okay, there it is. But if we're going to say, okay, there it is, we need to show that it for sure works. So let's try this out. Let's see, 0x plus ax. Well, by the way that we're dealing with addition in these in these proportions that we don't know are a group, that's what we're trying to find out. Well, what we would do is add 0 plus a. And that would be the new coefficient. Okay, well, we know 0 plus a, though. That's just a, whatever a is. And we get ax, which is what we wanted. So 0x plus ax is ax. So this works. So I believe that the identity property is true, so let's check that off. Okay, one more thing we need to find, and that's inverses. So whatever AX we use, we want to be able to pick out a ZX to make us add up to IX. But hang on, I can change this now. We want that to be 0x. That's going to help us. So let's think about some things that add up to 0. And the first thing that pops into my head is in negative numbers, the mutually assured destruction property of a number like 3 and its opposite like negative 3. If we add those together, they cancel out to 0. Same with if we started with the negative, like negative 4. If we add 4 to that, that gives us 0, and we can see clearly from a number line why this should be true. If we start at negative 4 and go up by 4, we get to 0. If we start at 3 and add negative 3, so we're basically applying this vector right here to it that looks like subtraction because it's adding a negative, we get to 0. So that's that mutual assured destruction property of two opposites. So we're going to use that. I'm going to say, okay, let's say the first thing we try is to let Z be negative A. Let's try that and see what happens. So we have AX plus negative AX. Okay, well, the way we would add those together is to say now we have A plus negative AX. But we know that that's 0, so that's 0x, just like we wanted it to be. So this formula is true as long as we say, okay, Z is whatever the opposite of A is. And every number has an opposite. Now, if we had 0 in the first place, that's a tricky one because it's its own opposite, but that's fine. Because if we had 0x plus 0x, that would definitely be 0x, combining those like terms. So it works right, even if we do something weird. There's no such thing as a number that doesn't have the negative number that goes with it. So this is true whatever direct proportion we had in the first place. So we have one more property that is followed, and it turns out that that's all the needed properties for us to say that this set under addition is a group. So I'm going to say yes. That's my final answer. I'm going to give it a star because I checked it thoroughly. I know I'm right. And I'm going to use the square with a filled-in interior, which is the mathematical symbol for I did this proof. It's not like a copyright or a trademark or anything like that. It just means that we've got everything there. Bam, look at it. We know this for sure. So we are absolutely sure that the group, that the set of direct proportions under addition is a group.